Here's a few comments on fault tolerance and other related um, latency type issues, synchronicity constraints. This slide points out an important issue, which is slightly controversial, which is what is an appropriate service level. Um, and that availability is obviously nothing is perfect. There have been some well-known cases like Netflix went off when Amazon lost service, and you express this guarantee, how important, how actual operationally important that is. I think it's still a little early to know how we want to do this. And there are some issues of performance because when you do these virtualized server consolidations, you're sharing a node between multiple applications, and so it's not so easy to guarantee that node gets a particular performance, because an application can be sensitive to disk I/O, to memory use, CPU use, and network use, and you really can't guarantee that you can give somebody 2 cores and maybe dedicated access to those cores. But if the other 6 cores on that node are being saturating the memory, those 2 cores can't actually do anything. So there is some important issues here which I don't think are very well understood. And I'm not certain they're critical at this stage, because I think people get adequate enough performance, because what you really care about is your performance averaged over time. So the fact that your 2 nodes got messed up by the 6 other nodes for some period of time is unfortunate, but maybe what that counts is the average level of messing up, and as long as that's small, then you're okay. So here is some examples for Azure of the service level agreement. We have the compute here's the guarantee on connectivity, 99.95%. Our computer center just went down yesterday in a storm, so all systems have some problems, and ours was a highly fault tolerant system. Azure monitors every instance, and it initiates corrective action if a node is dead. The storage is replicated so that if it fails, then it just goes to a different place. Databases are backed up and monitored, and your service bus and endpoints will have external connectivity, and your messaging is essentially guaranteed at some level. Again, these are not hugely high numbers here. These are 0.1% unreliability or 0.05% here. Those are quite serious failures, but as I said, you are forced to develop your software to be fault tolerant. Here's a much nicer reliability S3, and again, Amazon doesn't actually tell you what it does. I think the rumor is for the typical S3, it stores 6 times, and this gives you this huge reliability effect, and then average over a year the availability of the objects at any one time. Then they have this reduced. Then they found out that maybe some data really wasn't that important, because you can actually rerun it if it's a disaster. So they offered a somewhat cheaper, reduced redundancy storage, which has which has a bigger chance of being totally destroyed. And it's just done. I mean, one way to do that is install this a lot of times, say 6, and this not so many times, such as 4 times. And I say you might use this version if you could regenerate the data on demand if you had to, because then it would be better to pay less for your storage. When you look at fault tolerance, data is relatively easy to make fault tolerant. You, in some sense, replicate it in a few times. But then programs are not so easy, because when your programs are executing, they're sending information between each other, and it is not simple to just rerun the programs, because you're not quite certain what messages they were sending, what they've received, and what data they've written to disk. So once you have a data set which is finished, you can then worry quite straightforwardly about its fault tolerance. But running programs are not so easy. And the only easy way I know is actually more user-oriented. The user is instructed to save the state of his program every now and then. And that's particularly easy, say, in MapReduce, because MapReduces all communicate via disk. So if you capture the result of a set of map processes on their disk, that's a natural fault tolerance model, because the disk is easy to make fault tolerant. Well, the only issue here is they're rather slow, because everything has to be written to disk. But then MapReduce is designed for a problem for which that disk overhead is not important. In parallel computing, this becomes very tricky, because you have multiple processes running together. When one process breaks, all processes have to wait for it. So in some sense, the cost of a failure is multiplied the number of parallel processes. On a modern supercomputer, that'd be 1,000,000 way. So the necessary cost of synchronization and the fact that we have processes synchronizing makes the cost of fault tolerance higher for parallel processing. So loosely coupled processes are actually somewhat easier to make fault tolerant, and that's what clouds are aimed at. And so that's one reason HPC clusters are actually a big effort is to make them not to have faults, because the impact of a fault in high performance computing is pretty serious. You're running a million cores on a single job. If one of those cores breaks, then the other 1,000,000 minus 1 cores wait. So that's not good. Some commercial applications, if there are banking applications, they better not lose data. You'll be rather unhappy if your bank said, well, unfortunately, 1% of our people's money was lost because we had a disk crash. So commercial banking applications have to be completely fault-free. But some other applications, such as Netflix applications, the recommender engines, and you're looking at all the ratings to predict a new recommendation. If you miss out 0.1% of the ratings, or if you're doing a web search and you miss out 0.1% of the web, it will make very little difference. Of course, if the 1% you missed out was important, so if it was the Wikipedia entry for this particular query, then you'll notice it. But in general, you will not miss out the important parts. So a lot of the Web 2.0 cloud applications are pretty fault tolerant, and they do not need to worry too much. So that is dramatically different from the weather simulation, because the nature of the equations governing the weather imply lots of correlations. You cannot do a weather simulation and leave out the weather at Bloomington and try to get Martindale right. Those are Martinsville right. Those are nearby cities. You can't do that. All of these are highly coupled problems, and the mathematics of them are not very fault tolerant, and you cannot just drop part of the system.